Good morning. Welcome to another Ironside Take 30. This week's topic is on data science. And so that's why I'm here. I'm Pam Ascar, the Director of Data Science at Ironside. This week, we're going to talk about model evaluation techniques for machine learning. But I'm going to speak to this to the lens of a business leader rather than to a data scientist. So somewhat technical, but really my goal is to help the business leaders understand how models are evaluated and what they can do to ensure that it's good for their business and that it's not as simple and straightforward sometimes as, how accurate is this model. So we'll talk through all of those examples and different metrics and how they can put their own lens on it as a business leader. Now, before we get started, I always like to pause and tell you a little bit about Ironside. Our mission is to help clients use data to make better decisions about their business. We're a data and analytics consulting firm with over 20 years of experience with end-to-end data and analytics value. And so we have centers of excellence in all of these wedges and capabilities that you see on the wheel here, from advising and strategy to designing to building, and that's where a lot of the work with data warehousing, data visualizations, dashboard reporting, as well as data science and machine learning lives. But then we also have the capabilities to deploy and govern and manage long-term, whether that's data science or other platforms and solutions. So that's a bit about Ironside and who we are and what we bring. The agenda today, we're going to talk about some hard truths and just some examples about why it can be a little bit difficult to evaluate a machine learning algorithm with something as simple as, overall accuracy. And then because different modeling approaches have different metrics, we'll talk about classification metrics, and then we'll talk about regression. And really overall and throughout the whole thing, understanding when is a model good enough to move forward into operationalizing it, and how do I get the most use out of these models, and then sum up with some key takeaways. So I wanted to start with a quote that I love and I use very frequently from George Box, who is a famous statistician. He said, all models are wrong, but some are useful. And I think everybody kind of gets that you're never going to get a model that's 100% accurate. But saying this and repeating it really helps put things into perspective that the model is going to be wrong, right? And so you're not asking, is the model right or wrong? You need to ask, is this useful to me? What is our tolerance as a business for the error that it produces? Can we make use of it? And I think that just gives us a different lens to think about how we judge an algorithm and when we know whether we should move forward with it and make some use out of it. So I want to start with this example because clients, and I'm sure data scientists everywhere have this experience. They go to the business and the business says, well, how's that loan default model working out? What's the accuracy? Is it 95% accurate? Is it 90% accurate? And the data scientists may say, well, it's not that straightforward, and they want to talk about a few different metrics, and they hum and haw. And it's not because they're trying to be cagey about what the accuracy is. It's because it's just not that straightforward. And I think it's important for the business leaders to understand what they mean by that, and to understand how to really dig in and look at those metrics with the data scientists to understand how it's going to impact their business, and to make some decisions together with the data science team about how to optimize the model and what's going to make the most sense in your business. And so to do that, I'll show you this example of what's called a confusion matrix. And what we have here is really just plotting some actual scores against predicted. And this is what you would use in a binary classification model, like, is this loan going to default? Is this utility pipeline going to have damage if we dig here? Is this claim going to have an explosive amount? Is this claim fraudulent? And so these are just yes, no kind of models. When you look at this, what we're doing is not just looking at overall accuracy, but looking at the distribution of these false negatives and false positives. So of course you want the highest numbers to come out in those green boxes. What are true negatives, where it really was not, that loan didn't default and the model said it's not going to default, or it did default and the model said, yeah, you should take a look, this is probably going to be a default. Now this works really well when you have a case where what you're trying to predict occurs 50% of the time. which is what you usually learn how to do these models on in an academic setting. That's 50-50. And the reality is these things don't often happen 50% of the time. Loans don't default 50% of the time, thankfully. Damage doesn't occur 50% of the time. Machines don't go down 50% of the time. And so you're looking at things that occur maybe 5% of the time, maybe 3, maybe 10. And so it's just not that straightforward. So in this example, we have 100 cases of, let's say, loan default. And there's a 5% rate of default. So 5% of the time they default, 95% of the time they don't. And you see that we built a model to predict that. And 100% of the time, 100 cases, the model predicted that it would not default. So it didn't pick up a single case where it actually did default. The problem is that the model didn't really learn any of the signals associated with those 5 cases of loan default. Now, if we were to calculate accuracy for this model, guess what? It's 95% accurate. And I could just tell you that and say, hey, great news. We built a loan default model and it's 95% accurate. And you as a business leader could say, that's great. Let's put that into production and make use of it. But I think you can see the problem is that while having very high accuracy, this model is absolutely useless to you as a business because it's never going to detect the thing that it's designed to detect. So that's a problem. So I just want to use that as an example to say this isn't as straightforward as what's the accuracy of your model. And then we can look at how we might do that in other ways with other metrics. Now, there are many different types of machine learning algorithms. And so the ways that you evaluate them are going to be different. I'm going to focus today on just the first 2 because these are the ones that happen most of the time in business. Primarily, you're either building a regression model and you're asking things like how much or how many. So this could be how much loss is this claim going to incur? What's the revenue forecast? What's the cost estimation? What will the attendance at this event be? Those are regression problems. And then there's classification problems. So what category does this belong to? And those are some of the examples that we've talked about. Fraudulent claim, customer churn, loan default, machine damage. You're predicting it happened where it didn't. Now, of course, you could also have multiple categories and have a multi-class classification problem. But for simplicity, we'll talk about those binary cases. And I won't go into evaluating the others right now, since most of the time we're looking at one of these 2 situations. So back to our confusion matrix for a second. This is the best way to look at classification problems and to really understand how your model is performing with your KPI in your business. Let's first take a look at an example where it is a 50-50 split, which I don't think has ever happened in nature, but it's a good way to just use it as an example to understand some of these metrics. So instead of the overall accuracy, we can look at things like true positive rate. This is also called recall, and it's also called sensitivity. Maybe that's why they call it a confusion matrix, because they just have a lot of different terms. But I like to call true positive rate. What it is of all the loans that did default, for example, how many of those did the model pick up? So in this case, 50 of those loans were defaults, and the model detected 40 of them. So it's an 80% true positive rate. That's pretty decent, right? Now, when you're trying to predict something that doesn't happen very often, we often want to optimize for this, because the loan defaulting, damage on a utility line, a machine going down, an explosive insurance claim, they may not happen very often, but when they do, the cost is tremendous, right? And so you really want a model that can detect as many of those as possible. The issue is that you have to balance that with what's called precision. Precision is, of all of the cases that the model told you to look at, how many of those were actual yeses, right? So in this case, if this were loan default, the model says, look at these 45, you should take action on them. And 40% of the time, or in 40 of those 45, which is 89% of the time, it was correct. And you can think of the false positive rate as the reciprocal. So 11% false positive rate. And that's important because you can optimize a model to you can optimize it for the true positive rate, or you can optimize it for precision, but they do balance each other. And so you have to understand that if it's really important to get as many of those true positives as possible, you have to be willing to accept some of the false positives as well. And that's where it comes to the business to understand what is the cost associated with a false positive and what's the cost of a false negative. And so I worked on a model that was for insurance claims post-payment recovery. So they've already been paid, but there are hundreds of thousands of claims and teams manually digging through them, trying to detect where they could maybe get some money back. So this is health insurance. And if this claim was for an injury that was caused by an auto accident, perhaps they could go back to the auto insurance and get some recovery back because they should have paid for it. So the false positive tolerance is actually really high because they're already manually looking through hundreds of thousands. So if we can say, hey, here's 10,000 that you should look at, and within those 10,000, we can detect 80% of the ones that you could make money on, that's a huge win. It has a huge false positive rate, but it's okay, right? Because we're finding as many of those opportunities for savings as possible. And so it's about understanding the business, understanding how you would use it and what you would do with it. Now that model actually went on to a further step where they took some of those highest probability, most likely to be opportunities for claims recovery, and they sent them to an external firm to investigate. Now there is a cost. Every single one costs some dollars. And so your tolerance for those false positives comes down a little bit. And so again, you have to understand, how is the business going to use this? How's the model performing? And how do we optimize and tune this to make the most use of it and to get the most ROI? So if we look here, this is just another example where it's more imbalanced, right? Where 90% of the time there's, let's say it's utility damage. There's no damage to the utility site, and 10% of the time you dig and you damage a utility pipeline. And so you're trying to understand, in that case, how would you use that? So the utility companies could say, well, if the model flags this as likely to be damage, we're going to send a safety auditor on site, right? So according to this model, you would have to do that 15% of the time. Now there's obviously a financial cost to sending a specialist to be physically present on a site. And so you have to calculate that. What's the cost of sending someone to be on site in 15% of our digs? On the flip side of that, only 10% of the time digs happen, and this model detected 50% of those, right? 5 out of 10. So what's the cost of 50% of those damages if you could identify them now and prevent them, right? And so does that cost of identifying 50% of the damages outweigh the cost of sending a specialist to 15% of your sites? And really, that's how we try to evaluate this and make sure that it's useful to the actual business and how they're going to deploy the model and use it. So one more walking through of confusion matrix, because I think this is important, and this part is probably less known. What does it mean to actually say that something is a yes or a no on this model? Because the machine learning algorithm doesn't actually provide you with a yes or no. It's not going to say this claim is fraudulent or this claim is not fraudulent. What it's going to say is, here's the probability of it being fraudulent. And what you do with that probability is up to you as a business leader. And this is why it needs to be a business discussion paired up with the data science team. As a default, we say if the probability is greater than 50%, then we put you in the yes column. If it's less, we put you in the no. But again, that is perfect for cases where what you're trying to predict is perfectly balanced and happens 50% of the time. And in reality, that's not usually the case. So if we look at this example again, where we're trying to find utility damage, it happens 10% of the time. And we have this model here. I have a table here on the right that shows the top 3 of those 100 observations. And they got probability scores of 10%, 37%, and 82%, right? So the bottom one says this dig ticket, right, where you're going to go and do a dig, has an 82% chance of having damage at that site. So it gets a yes. Now that's if we use that threshold of 50%. Let's say we drop that to 30, because we know this only happens 10% in reality. Drop it to 30%. You see the second one now that had a 37% probability now goes into the yes column. So there's a few things to point out there. One, you notice if I go back, 37%, 37%. We're not changing the model itself at all. This is not about manipulating the model or adjusting it or being too heavy-handed on the model. The model tells you what the relationships are and what its probability is. You as a business are saying, my tolerance for false positives is pretty high, so I want to lower that threshold and let more false positives in so that I can capture more of those utility damages. Because if you look at the confusion matrix, instead of identifying 50% of the damages, we now identified 80% of them. Now in doing so, we have more false positives, right? So if I go back, you see here in the predicted yes, the model told us to investigate 15 of those and 5 were damaged. Now we have to investigate 28 of them. So again, it goes back to, we got an extra 30% damages detected. What's the cost of that? And what's the cost of sending an auditor to 28% of the sites? So this is not a yes, no, right, wrong, accuracy has to be above 90% kind of situation. This is, what are the false positives, false negatives? What does that look like at different thresholds for the probability score? And what is our tolerance for false positives? What's our tolerance for false negatives? What's the cost of those for our business? And then having that discussion together between the business and the data scientist to optimize the model for your needs. So there's probably more confusion matrices than you'd like to see ever, but a few other metrics for classification that we use. AUC stands for area under the curve, and it refers to what's called an ROC curve. And really this at a high level is just a measure of how well the model discriminates between those two classes. And if you plotted the curve, which basically just plots false positive rate against the true positive rate, if it's 50%, you'd see this red dotted line. That just means you're no better than chance at guessing which ones are going to be damage or fraudulent claims or default loans. But you see these models, the green, the orange, and the blue, it starts to get better and better. 1.0 would be perfect. We know it's not going to happen in reality, but AUC is a nice, fairly unbiased metric that you can use. And, usually we say, let's start at a 0.75, right? If we can get an AUC of 75, that's a good place to start. Of course, you want it to go better and better, but it's not as biased as accuracy is to the balance of the model. And another way we look at this is the top 10% rate, which is very similar to adjusting that threshold, right? Instead of saying anything over 50% is a yes. Instead, what we do is we say, let's rank all the cases by their probability score. What's the probability of damage? And take the top decile. And that top decile could have very low probability scores, but let's take the top decile. And within that top decile, how many of the actual damages did we correctly identify? If we got 80% of them by just pulling out the top 10%, that's a pretty good model. And that could be valuable, again, balancing the cost of those false positives. So those are just two other ways that we look at models. I'm not covering every evaluation metric out there. There's a lot of other ways to look at it. Log loss would be considered. And we also don't just take one metric, right? So this is a process that data scientists would go through of looking at this in a lot of different ways. And again, hopefully relating that to the business. And then I want to talk about regression problems. They're a little bit different. So here we're not really evaluating how often we're right or how often we're wrong. We're looking at the degree of wrongness because we're trying to predict something continuous like revenue or claim loss or event attendance or student enrollment, right? And so the plot here you see is just a simple example of the red line is a linear regression line. So that's essentially what the model predicts. And the blue dots are what the actual scores are. And you see here, I drew these black lines. Every single one of those blue dots is going to have a residual, which is just a measure of how far off you are from the red line. And so the residual is just that delta or difference between what we said it would be and what it actually was. If June revenue was 50,000, but we predicted it'd be 46,000, right? Then we're off by 4,000. So the mean absolute error is just the average of all those absolute values, plus or minus, you know, $5,000. Is that meaningful or not? You can't say, and a data scientist working in isolation can't say if on average being off by $5,000 is important. Is it valuable to be off by 2 minutes in a client wait time prediction? Is it valuable to be off by 10 students in a student enrollment model? That's very hard to say, again, if you isolate yourself from the business. And so it's important to have that conversation between the business leader and the data scientist to say, here's what our tolerance is, here's what a model would need to have to be valuable to us as a business. One more point about residuals, one other thing that a data scientist would look at is the distribution of those residuals. So if you standardize them at 1, what we basically are looking at here in this bottom plot is how often do you overestimate and how often do you underestimate? And so it should look something like this, where you're equally as far off above and below. And at lower numbers and higher numbers, everything's kind of an equal box there, and you're not seeing some spread where at some point you start to get really far off. So just another way that a data scientist would look at those residuals and make sure that the model's being fair. And then R-square. I think this is important for a couple of reasons. R-square can be challenging for people to understand. I'm a visual person, so I like Venn diagrams. Some people don't. So take this if it's helpful. But R-square is basically just a measure of how much your model knows about the thing you're trying to predict, right? If you're trying to predict revenue, you've got to add predictors. So X1 and X2 are predictors of Y. So if you look at these bubbles and you say, Y is everything we know about our revenue, or everything we don't know, right? It's everything that impacts revenue. And every time you add a predictor, it's probably going to take up some of that space because it knows something. It helps you predict Y. And you add a second one, it helps you know. Your predictors themselves overlap a little bit, and they share some variance. So here in the space called B and D, that's where those two overlap and don't offer a unique contribution to Y. But A and C is where, you know, each predictor can help you learn more and more about Y. Now, this is helpful, one, because once you build your model, R-square can tell you all the things that impact this. How much of it did you learn? How much does your model know? So if you have an R-square of 0.65, you've captured 65% of the variance in that metric, revenue or student enrollment or event attendance. I use this a lot for evaluating, adding extra information to a model. So if I'm doing third-party data enrichment, for example, if we look at another Venn diagram here, we have again Y, what we're trying to predict. We have X1 and 2, those are my internal data points. They help me learn a bit about Y. Now I'm going to add Z1 and 2, so maybe that's external data that I added. R-square can help me understand, did they add meaningfully or not? So here's an example. If I want to acquire some third-party data and I just want to evaluate it first, I enrich my internal data with it and I build a model. Maybe that model has an R-square of 82, right? That's great, and I'm really happy with my third-party data, and you know, maybe I go for it and I buy it. But here's the thing, I need to know, did that actually contribute more information, or did it just overlap with the data that I had? So what I would do is I would build that model exactly the same way, but without third-party data and with that third-party data. And so if without the third-party data, my R-square was 81, and with it, it's an 82, I start to understand, yeah, the model's great, but that added effort didn't actually contribute over and above what I already had in there. Now, if my R-square went from 65 to 82, I say, wow, that's a significant amount of information that the third-party data actually contributed over and above my internal data. And so R-squared to me is very helpful in that way to validate the cost of purchasing external data or to validate the effort of getting something else and adding it to a model. So I'm going to quickly talk about when is a model good enough. I've kind of hinted about some of this. You've got to balance the cost of those false positives and false negatives, the cost of each unit of a residual, and ask yourselves, is this better than what we have today? How would I operationalize it? How would I use it? And I wanted to give an example of making something AI informed rather than AI driven. Excuse me. I think people think a lot about AI as automating decisions away, like your spam mail, and no one ever sees it. And the reality is, you can balance those false positives in a way that help you use this in an AI informed way. So what you're looking at here is a damage prevention risk application. So for that utility damage example, you see a specific ticket gets logged, it gets scored in a model, and those blue bars over here say, hey, this has a threshold of likely to be damage above whatever threshold the business set. And so it says you need to schedule an auditor to be on site there, right? It's not automating something, but it's giving you more information and it's giving you a way to take action, because as someone looking at this, you could say, oh, this got flagged, why is that? And I can start to dig into it and look at the reasons. And I can add my human intellect that, oh, maybe the model was wrong here. I see why it got flagged. So again, it's AI informed, and that helps you, again, to be okay with a little bit more error and a higher false positive rate. This is another example from underwriting, where in the black part down here, we provided AI-driven risk scores of a claim happening. So we're not saying, hey, this is risky, so automatically bump up the premium or don't renew it. We're saying, hey, underwriter, there's a 16% chance that this policy will have a claim in the next 3 years. So, you take that information and you take the key metrics down here, the reasons why the model flagged it, and make some informed decisions. So it's about adding information and doing analysis on a vast amount of data faster than a human could to help the human make decisions. So I'm just going to sum up now.
Before you summarize, I just had a quick question that came in. Somebody asked, well, what if the model's not good enough?
What if the model's not good enough? When you make that decision, I would say pivot away. So, in AI, you don't want to iterate forever. Data scientists they don't want to let go of a model. They want to make it better and better and better, right? And you can iterate forever. I would say make it as good as you can and make a decision. Either put it into operations where you can start getting the benefit of it sooner, even if it's, a small benefit, get the benefit, or drop it. And then the data scientist can take on another use case. But don't spend too much time. Don't spend 6 months just hammering away at a model that you're not getting any benefit for. Either put it in production or move on from it and find something else, because I'm sure there are plenty of other use cases in the business that your data science team could spend their time on. And I can leave these tips up here if there are more questions that I could answer, because I know I went a little long on time today.
There was just one other one. Are there any metrics that that going in, you should know you should always be above a certain threshold?
It depends. There's always benchmarks like AUC. I like to see a 75 before I say, like, okay, this is worth iterating on and trying to improve. Otherwise, maybe there's some problems. Accuracy, I think I explained the problem with just looking at a threshold and going, I've got to have accuracy above 85%. And so I think most of the time it's not that straightforward. AUC is a good one to look for. R-square, people, they want to see that above a certain level, but the academic in me says, you can go very low on that and still have a very good model. So.
Great. If you just want to summarize the takeaways, that would be terrific.
Yeah, so my first takeaway here just kind of speaks to the comic strip there about accepting something being AI informed. AI driven, I wouldn't go AI driven and automate something away unless the cost of being wrong was very, very low and your model was fairly accurate. But you can take something that's okay and that meets your requirements for false positives, false negatives, or residuals, and use it in an AI informed way in those 2 examples that I just showed by offering more information. Again, make it a business decision and discuss those success metrics early with the data science team. Data scientists are often siloed from the business. They don't know your KPIs as well as you do. They don't know the ins and outs and the nuance, and they may not understand how you would actually use this. And so have that discussion very, very early on. Take what you can learn from models. So sometimes it may not be worth putting something into deployment and operationalizing it, but you can learn from what were the key drivers of that model, right? And also, you could learn about your data and maybe some changes that you should make around governance and improving data quality. So there's a lot of learnings that you can get there. Accelerate time to production, then iterate and improve. So again, don't spend 6 months iterating on a model, make a decision, either put it into production, and then you can, have a round of improving it after it's been out there for a while, or drop it. And in that last one, let go of underperforming models, right? Pivot away and look for other use cases if it's just not going to bring you the value that you need, because sometimes AI just doesn't do that. So thank you for sticking with me a little bit over on time. I appreciate that. Happy to answer any other questions, but I appreciate your time today. And I hope everyone has a great Thursday. Debbie, are there any last minute questions I can answer before we go?
Nope, we're good. Thanks, and everybody have a great week.